My name is Yasin Zafar. I am a student of Advanced Engineering Management, and today I am presenting my MSc research and investigation into a low power AC to DC converter topologies, efficiency design, trends, and material advancement under the supervision of Dr. Rose Wyatt Millington. First of all, we can start with the introduction. The demand for the electricity is rising quickly across the world. The International Energy Agency estimates that electricity demand will increase by around 25% by 2030. This growth is due to the following factors such as industrial growth, digitalization, electric transport, and rapid urbanization. Low power AC to DC converters are very important in this scenario. These converters are used in almost every modern devices such as mobile phones, laptops, LED lighting, renewable energy system, IoT devices, and even in electric vehicles. The job of this converter is to change alternating current from the grid into a DC with electronic devices need to operate, even though these converters are small, but they are used in billions of devices. So even a small improvement in their efficiency and can result in a huge global energy saving and reduce the carbon emission and support the sustainability goals. This is why the research focus on comparing converter topology and semiconductor materials, looking at efficiency, cost, design trends, and performance advancement. Further, we can move up to aim and objectives. The main aim was to investigate low power AC to DC converter topologies, was focusing on efficiency, design trend, and material advancement. To achieve this, we have 4 objectives. First of all, to benchmark performance includes comparing efficiency, thermal performance, and EMI of converters using silicon, GaN, and silicon carbide at a low power of 15 watts or even less. Secondly, to compare converter topologies, includes such as buck, flyback, and LLC resonant converters, and identify which topology is the best for low power application like IoT devices and renewable systems. Third, we have to evaluate the cost effectiveness, check if wide bandwidth semiconductor like GaN and silicon carbide can be a practical alternatives to a silicon in real consumer products. And the last one was to propose hybrid design. Combining the high efficiency of switching converters with the low noise of a linear converters, which can be very useful in sensitive applications such as medical devices and audio systems. These objectives gave a clear pathway to carry out the research and also helped in the testing the hypothesis that GaN-based LLC resonant converters perform better than silicon-based flyback converters at 15 watt. Further, if we can move up to the literature review, the study was based on systematic literature review. This means that it is not a designed hardware prototypes. Instead, it's carefully reviewed by published studies. The process was done in the 4 steps. The first, I defined the scope, low power converters of up to 15 watts. Second, I search academic database like IEEE Explorer and Science Direct, and then we have a Google Scholar. Thirdly, I applied inclusion and exclusion criteria. Only study with the simulation result or experimental result were included. Finally, I extracted the data on key factors such as efficiency, EMI, thermal behavior, and design complexity. From the literature review, some key findings appeared. Silicon converters are low cost but face efficiency limits. GaN and silicon carbide provide higher efficiency and power density. Among topologies, LLC resonant converters show the best efficiency and EMI performance. But in the real world, flyback converter remain the most common because they are simple and cheap. So the literature provides evidence to compare semiconductor and topologies systematically. Further, we can move up to the methodology. Basically, the methodology covers the 4 points. The point 1 was the research approach. The research was carried out systematic literature review, as mentioned above. This means I didn't use the build hardware prototype. Instead, I collected and analyzed results that were already published in academic journals, conference papers, and technical reports. The second point was defining the scope. The scope was limited to low power AC to DC converters up to 15 watts. This ensured that The focus remained on applications like chargers, IoT devices, small renewable energy systems rather than a high power industrial system. The third point was the literature search and selection. I searched the academic databases such as IEEE Explorer, ScienceDirect, and Google Scholar. From there, I applied inclusion and exclusion criteria. Only studies that reported simulation or experimental results were included. Papers that were purely theoretical or without data are excluded. And the last point was data extraction and analysis. From the selected studies, I extracted key performance results including efficiency, electromagnetic interface, EMI, thermal management, and design complexity. These results were then compared across different semiconductor materials, silicon, GaN, and silicon carbide, and converter topologies like buck, flyback, and LLC resonant. And then further we can move up to result outcomes and discussions. First, we can present the result and outcomes from the comparison of semiconductor and the converter topologies. The outcomes are GaN-based converters are the most efficient. They often reach efficiency above 95% and they allow design that are smaller, lighter compared to silicon. LLC resonant converters perform the best overall. They have very high efficiency, 94 to 97%, but they have low EMI because of soft switching. But they have a good performance under light loads. Then we have flyback converters continue to dominate mass market products like mobile chargers, but their main advantages are simplicity and low cost, even though efficiency is lower. Hybrid design were found effective in sensitive systems. They combine the efficiency of switching converters with the low noise of linear regulators, which is very useful for medical and audio devices. These results confirm the main hypothesis: a GaN-based LLC resonant converter perform better than a silicon-based flyback converters at 15 watt. The only trade-off is the GaN-based LLC design are most costly and even more complex. If we can talk about the discussion, we can discuss the results. These results highlight several important trade-offs. First of all, efficiency versus cost. GaN plus LLC converters are the most efficient because they're expensive. Flyback converters are less efficient, but still dominate low cost consumer market. Performance versus simplicity is the second point, where the buck converters are simple and efficient, but they do not provide isolation. Flyback converters provide isolation and low cost, but suffer from EMI. LLC converters give the best performance, but they are more complex to design. Then we have a thermal management. Wide band gap devices like GaN operate at high frequency. This creates hotspots in small areas. Thermal management is essential to ensure reliability. Then noise and EMI. Hybrid designs are valuable for noise systems like medical devices and audio equipment, where the both efficiency and the quiet operations are important. So there is no single best solution. The choice always depends on the application requirement. Then we can move to the ethical consideration. Ethical consideration says that the study was based on systematic literature review. No experiments with human or animal were involved. No sensitive data was collected. The main ethical responsibility was academic honesty, referencing all sources correctly, using the Harvard style, and avoid the plagiarism. Therefore, the research carried out no ethical risk. Finally, to conclude, this research provides a practical evidence-based framework to help engineers select the most appropriate low-power AC to DC converter topology. The conclusions are GaN with LLC resonant topology is the best technical option for performance. Flyback converters will continue to dominate cost-sensitive markets. Hybrid converters are the best for noise sensitive applications. If we can talk about the further research should focus on, so we can discuss that the building real prototypes to confirm these results, exploring new control strategy to improve efficiency further, and considering the sustainability and life cycle analysis in converter design. So if we have to conclude, the key message was just that the best converter design is context dependent. It depends on whether the priority is a cost, whether your priority is a cost, or whether your priority is performance or the noise reduction. Thank you.